I'm Yannis Hector. I'm a software engineer at Salesforce. I've joined the search team 4 years ago in the Grenoble office in France.
I'm Smiley, working with Lucidworks working with Salesforce via Lucidworks. And I recently joined Salesforce full-time.
So we want to present you the project we have been working on for 1 year now to be able to query hundreds of fields at the scale of the Salesforce platform. Before we start, we would like to thank our colleague Bruno Roustan, which has a scheduling conflict and cannot be there, but he has been deeply involved in both this project and this presentation. So here is the agenda. We will start with a bit of context of Salesforce. Then we will detail why it's difficult to query hundreds of fields. We will then detail the solution we have implemented and finish with a few performance charts. So a little bit of context. I'm not sure you are familiar with Salesforce. One of the key points of the Salesforce platform and a fundamental piece is the multi-tenancy. At the Solar level, it means that we allocate a core for each and every customer. And for biggest customers, a single core cannot handle all the data. And we have a split strategy based on the disk size used by the index. So as soon as an index increases 500 megabytes of data, we split it. So biggest customers can have thousands of cores. So it means that at the Solar level, the transient core cache is full with a lot of small cores. And that's why we must be very careful with resource consumption to serve every queries, every indexing, and also the memory used by every cores. The second point is about docs diversity. So Salesforce is a well-known CRM, but it's much more. And every customer can customize, create fields for standard entities like contacts or accounts, but they can also model everything they want. They can create objects, create fields, hundreds of them, and we need to index everything that is relevant in the search context. And it's a lot of structured data we have to take care.
Mm-hmm. So, searching hundreds of fields. To be clear what I'm talking about, Solar has a EDIS Max query parser. Most people use it or perhaps create something custom that's similar. It has a QF parameter where you list the fields you want to search with an optional boost as well. You don't see that on the slide right now. And here we see field F1, F2, F3. The names are notional all the way up to 150. And this may seem a bit crazy. If you were to walk into some new search project and see something like that, you might think something's going wrong here. Maybe you didn't model your data correctly. It's not going to scale. Maybe we should just use some catch-all text field and search that instead of searching so many. Well, sometimes you just can't do that. There are use cases where it really requires that you be able to search the fields individually. And a big one is being able to have field-level security, where certain people can search certain fields, others cannot. And if you have a very dynamically defined way of expressing this, where you can't simply bucket users into these three groups and have maybe three catch-all fields. No, you can't do that. Very dynamic. You want people to be able to change these settings on the fly and have it immediately respond to that. Then you have really dynamic rules, and you really kind of need to search these fields individually. That's a big one and a motivating example for us. Another is relevancy. If you have fields indexed separately, you have different statistics on each one that can inform the relevancy. And a big one, and it's easy to underestimate this, is that if you're building a search vertical, if you're using Solar to build search at your site, you have a lot of technologies at your disposal to do that. But if you're providing a search platform that other people build on top of that to build their experience, you need to offer. You want to offer a broad set of capabilities to everybody on top of your platform. You want to make them all happy. If they want it, we want to make it possible. If they want to search 150 fields, then you want to say yes. You don't want to say no. They might look at one of your competitors, perhaps. And to make this more real, like why? Okay, what's a real-world example here for 150 fields or more? And the best motivating example to me I've seen is where the document represents a survey of answers. So imagine a long survey, a survey where we probably don't want to fill out that has 150 answers, but you can see that, okay, maybe with a bunch of answers, maybe some of the answers are multidimensional, so there's multiple fields. You could see how, we really might want to have that many fields, especially if everybody's filled out the survey. You want to see what words people used in certain fields. We need, we can't get around this. We really do need be able to search many fields.
So let's have a look at what happens when we increase the number of fields to query. So here is a basic query today in our platform that only target a single field named body. So we used to have a Boolean query for the three terms big, bear, and cat with default AND operator. So we have must clauses between them. And we also use a proximity boosting, PF2 parameter, to boost documents where the term sits next to each other. So it generates also two other phrase queries, big bear and bear cat, that generates two additional term queries. So in the first phase, we need to seek the index and seek each and every dictionaries. So it means we have to process 7 term queries and 2 phrase queries. In the opposite way, then we will have the second phase where we need to compute the score of matching documents and merge them at the top level. Now, if we increase the number of fields, let's say now we target 2 fields, F1 and F2, the Lucene query changes. And you can see the dismax layer appearing there. If you're not familiar with dismax query, a disjunction max query is basically, it generates the union of the subqueries. And it scores the document with the maximum score as computed by any of the subqueries. So for example, here it means that we can match big, bear, and cat in various fields. And we will have finally the documents. So functionally, it's really equivalent to a single catch-all field. So by doing so, with 2 fields now, we double basically the number of term queries and phrase queries, and we have these 5 dismax queries on top of it. Same thing for scoring. The scoring phase, of course, is impacted in the same way, and we have 2 times more scoring to process. Now, if we query 150 fields, we see that the Lucene query starts to become very big with a lot of term queries, more than 1,300 phrase queries. So the complexity of such queries become a problem. Even more, when you might know that we have to do the seek for each and every segment. And today in Salesforce, in mean, we have around 20 segments for each course. So it means we have thousands of seeks to perform now to get the answer of the query. So I have a little problem with layout because I changed of laptop. But yeah, so we measured the performance with a naive approach, just using Solar as it is and increasing the number of fields. And basically, we observed that the latency and transient memory used to serve the queries and to answer are correlated, and there is an x20 factor to have the answer. With profiling sessions, we detected that most of the time was lost in the term dictionary seeking phase when we need to load blocks to scan terms. And we also observed some degradation in the query parsing phase. Another important point was the retained memory, because we need to load 2,000 cores in memory. And with the naive approach, the retained memory for each core can be triple. So we cannot go that road. And our main challenges with this project was clearly to come back to performance equivalent to a single catch-all fields. And we knew that one of the biggest driver was the number of segments, so we decided to divide it by 2. And we also needed to control memory expansion and have low memory usage.
So, naively searching many fields, it works, but it's slow. And Yannis described in detail a bit what's involved, and you can get a sense of why. One aspect is the query parsing. I'll explain in a moment. It's not so much the literal parsing, it's analyzing the text of the words for all the fields. And then there's the query execution, which is where the bulk of the time is. But there's query parsing, there is query execution as well. And you see the fields as involved in the algorithmic complexity in the query parsing and in the query execution. You see the segments as a factor. The disjunction max queries on the slide is basically the number of query clauses that you see in your query. That's pretty much constant. We're not going to change that. And honestly, in Lucene, this is a bit of an anti-pattern, which isn't to say that we shouldn't do what we want to do. It's good to know you're rubbing against the grain, that this is not something that Lucene is optimized for. We're going to hit some snags along the way. Some of those snags are going to be easy, quick wins. Some of those are going to be hard fought. And in addition to this execution aspect, as Yannis mentioned, it uses a lot of memory too. We have to do something about that. And we're going to review the process of Lucene. We're going to flow based on the order in which Solr and Lucene execute this, not necessarily in order of effort. The hardest part was really in the terms index, which is the last part we'll mention. Next. So in query parsing, one of the things that the query parser's got to do is got to take a word in your query, like big, and it's got to enumerate the fields that you want to search over and run it through the analyzer to stem it, lowercase it, do all that processing. So if you have 150 fields, it's doing that 150 times. But if you look closer at your fields, you might notice that most of them actually have the same type and have the same analysis, so it's very redundant. If your QF only lists 10, 20 fields, this is kind of no big deal. But if you got 150 fields, it is a big deal. This is a relatively easy win. So there's all this analysis going on, thanks. And because we control our query parser at Salesforce, it was relatively easy to recognize this optimization and figure out which field types are in common and execute it per field type instead of per field. There's another aspect of this wasn't just the typical words in a query like big or whatever. It was also the wildcard queries there was a similar aspect to this as well. That was a little bit distinct from how we did this. We had to make sure that we built one so-called compiled automaton in Lucene instead of doing it 150 times over. And the next part is the segment count. So normally, in a typical search app, the segment count is not really that much of a big deal in terms of the performance. It can be a big deal in certain key cases, but usually it's not. If you're searching many fields, you start to notice that this really does matter. We did tests where we searched a smaller number of segments and larger, and sure enough, it was a factor. So we targeted this as something that we want to do something about. There's no free lunch here. We're going to try and merge segments more, and that's going to come at an indexing cost. But we're willing to pay for it if we can get the search benefits we want. So the indexing pattern at Salesforce is there's a lot of updates coming in sporadically. Imagine someone looking at a page of data and editing something and saving, and eventually it goes off to a Solr index and it gets saved. And that might be one little document that arrives in an index. That's a segment of just one document. And sure, we batch it every 30 seconds, but still, these are relatively small. So we got a lot of these tiny little segments. And by the way, we replicate it as well. So the default merge policy in Lucene, tiered merge policy, it will merge 10 segments at a time. 10 is configurable, but the number that you choose is the number that it merges at a time. Not less, not more, always that number. And it'll always merge 10 at a time. And it does have an internal notion of the idea that, if we have lots of segments, then maybe we want to merge more often. So there's a threshold, but it's still going to merge 10 at a time, which is not necessarily a cheap merge. We want cheap merges. Also, the merge scheduler will do it asynchronously, which is to say that once the merge policy figures out what we want to merge, it will get merged in the background, and eventually you benefit from that merge in the background. It happens concurrently in another thread. That's how things run. So I worked with a team at Salesforce. We worked on a merge policy that basically extends the Lucene merge policy, and it will more eagerly look for the smallest segments. And with a variety of rules, we'll figure out when we think it's worthwhile to do it. It has to be below a certain size. We don't want extreme lopsidedness in sizes that we're merging. And it will merge these. It'll merge as few as 3. Right. And furthermore, we sometimes will merge these so-called cheap merges. We do it synchronously, which is to say we do it when the merge scheduler is something that we extended. And if we see that we have a cheap merge, we don't want to do it in the background. We want to do it now. Because if the merge is cheap, and if we do it now, we can save on the replication that happens to another node. In other words, that newly flushed segment might never end up being seen by the replication if we merge it immediately. And our goal was actually, my personal goal was 25% reduction in segments, and we was very surprised that we got 50%. We are paying for it, though. So here we see on the slide a performance profile of the number of segments on average. And of course, it changes as you add data. It's also kind of nice to see on the right the number. The blue dots are our current merge policy that we've just implemented. It's more stable because we merge more often the smaller segments. The degree of variation of number of segments you have is also more low, which kind of helps with the 99th percentile kind of situations. Next. There is a cost. One of those costs is indexing latency. There's other things we could measure. We're also concerned, we have more measurements to do about the replication that we're doing, because if you merge more, it's not free. You're going to pay. So it's just a matter of how much and how much benefit you're getting. Next. So as we start into the biggest, most difficult part of the challenge, the terms index. It's important to realize that Lucene, its data is organized in a certain flow. It's organized by its fields first. And once you get to a field, then you can look up the terms, then you can look up the docs, then you can look up the positions, and then you can look up payloads if you have them. And if we want to address, for example, the memory constraints that we have, we don't want, from going from one field to 150, we don't want to have, you can understand that a given word is going to be found in multiple of the fields. So by having one term dictionary, we can get savings. So what we want to somehow do is move the field differentiator, if we can somehow, move that distinction further down so that we have like one virtual field. It's like a catch-all name. And somehow with tricks that we haven't yet described, with some tricks, we're going to figure out when we do the field differentiation at a later time. So we want one shared term dictionary that's going to be smaller than 150 of them. So there's how to do this. So again, why? It's going to save a lot of memory. And with some caching, it'll save some CPU, which Yannis will get into in a bit as well. But where and how? So we're about to describe how we did it, which will involve a field ordinal tail of the terms at the suffix at the very, very end. We sort of embedded an ordinal into the terms. That was one path. That was the path that we ultimately took. There are other paths that others might take, where the journey that I'm describing here is the path that we've taken at Salesforce. It's not necessarily everybody's path. For example, perhaps one of the easier things to do might be to stuff it in a payload, because that's a very well-supported API that Lucene offers. Another idea I was kicking around was using position windows, where if you have one field that has one field in Lucene, but it's actually from 150 other fields, you have different windows of positions of your data, and if you somehow track what those position windows are, you can use tricks with position windowing. So there's different trade-offs here. In particular, I think the further down you do your trick, the more cost you pay if you have a field-differentiated query. By default, Lucene puts it at top, and thus, if you query for a particular field by a value, it's optimized for that. It's optimized for field-differentiated queries. It's not optimized for 150 fields. Next. So as we get into the rabbit hole of how do we do this really technically difficult challenge, it's important to get a sense of what is Lucene doing, what's happening with Lucene under the hood, what are the key things you need to understand of what's inside Lucene. And every Solar core has associated with it a index directory, and the Lucene API for that is the index reader that holds it. It's a Lucene directory and Lucene index reader hand in hand. And that is composed of a number of segments, and each segment has what's called a leaf reader. If you look into the leaf reader, that's what has basically all the data associated with the document, from the terms index to the stored value, doc values, all kinds of data. Pretty much everything is in that segment, in that leaf reader. The particular data we're interested in here is called the postings format. That has the terms index and the postings data. And the first thing it does is immediately organized by field first. Once you get into a particular field, then we have all the data for that field. We have the term dictionary, which is composed of the prefixes, which are held in memory, and the suffix parts, which are held on disk. The API does not strictly say that you should do this. This is what the default postings format does. So here we can see bet, bear, big, bigger. There's a variety of words that are encoded there, part of it being the prefixes, part of it being the suffixes. Once you get past the term itself, you have to know how many documents do you have, and then you actually list those documents. And per document, you can list the positions that that word was found in at that document. Optionally, you may have payloads, maybe you don't. But that's part of the big picture here. Next.
So let's step back a little. So far, we only detailed what we did for the number of segments. And David just detailed you the internal structure of the index. So we can now detail our solution for improving terms index and especially the seeking phase. So let's step back and have a look at our very complex queries. So to be perhaps clearer than before, today, when we have one dictionary per field, we need to search the big field, the big term in the field one. So we have to load the field. We have to traverse the prefix tree. And then we have to load the suffixes block and scan every suffixes until we match or not. And if we have a match, we will then fetch the postings, docs, positions if needed. And we have to do this for every term queries, for field 2 and field 150. And for proximity boosting, we will have the same term queries, and we will still traverse the tree and do the same thing again and again. So it means we have thousands of prefix tree traversal and access to doc IDs. So the big idea that David mentioned is to rely on the existing postings format. Basically, it's block tree, terms, reader, and writer. And we use a single one. And we encode the fields information at the end of the term. So we revert now. We have the field information after the term. And to do this, we introduce a virtual fields layer where we map every field to a suffix. We use a 0-byte separator first to ensure ordering and have good performance while merging. And so by doing so, we see that we have only one prefix tree. So we save memory by sharing this prefix tree. But for latency, we don't have any impact so far, because we still need to traverse the tree, load the blocks, load postings, each time we have a term query. So second phase, before going to second phase, few other memory tricks, memory issues with it, and we had to decide whether or not we have some trade-off to consider. And the first one is indexing norms. And indexing norms are heavy in memory, and it's not useful for every field. Some fields doesn't deserve any indexing norms because it's just one or two terms. And also the query results cache basically stores the results of a query, and the key is the query itself. So as we detailed, query with 150 fields are big, and it can retain megabytes of memory. So you have to design and improve the query results cache. Second phase of the optimization of the seeking phase is to introduce a seek cache. So the idea is to have the information and to do a seek only once per term and field. So first time we will search for big in the field 1. We will traverse the tree, access the suffix blocks, load the postings, docs, and positions that hits, and we will keep this in the seek cache. So it's not really a cache. Its lifespan is basically the time of the request. We initialize it during the create wait phase of the index searcher, and we clear it after the index searcher search method is finished. So dashed arrows there means we have a hit cache. So for the proximity boosting queries, we will issue the same queries again, big for field 1 or any of them, and we will simply get the information in the seek cache. No need to traverse the tree, load the suffix blocks, and so on. So by doing so, the degradation factor is greatly lower. One of the drawbacks there is that if you have a lot of matches, we can cache a lot of information there. Last optimization was to introduce a new layer on top of the query to analyze the fields and terms we want to target. And basically, we introduced in the rewrite methods of every Lucene queries object we use an information to gather and collect the fields we want to access per terms. So first time we will access we will search for big in the field 1. We will then look at which other fields are needed. And we will position to the first field, big 0 byte 1, and then we will scan all other fields and fetch all the information needed for other fields. And we will keep them in the seek cache. By doing so, we are reducing the number of seeks and scans a lot, and we will have only to do this for every terms. So now we basically have only 3 prefix tree traversals, larger scans for sure, but we access also positions and doc IDs correctly into a unique scan. So now we are getting closer to the performance of a single catch-all fields.
Scoring occurs after Lucene has seeked the term dictionary on all of the fields involved. It's then accumulating the documents and scoring it as it goes. The number of fields was a factor in this part, relatively small. We found a couple surgical things to improve, and a small one was computing the statistics. It needs to get the statistics of the field and the term as part of the relevancy, and we identified a relatively quick win in Solr for that, and that was already committed to Solr, in fact. Next. And okay, so how did we all do that? How did we do all of that in code? So we developed a new postings format called shared terms postings format, and it wraps Lucene's default postings format, which we basically didn't touch. But by wrapping it, it saved us some effort of needing to do surgery on the default one, which is a very complex postings format, I might add, block tree. We introduced this virtual fields tracking. We need to track these fields to an ordinal number internally. We didn't use Lucene's ordinal numbers for the fields. We used our own for certain reasons. We also needed to track the stats per field as they were flowing into. So even though we're delegating and sending everything through to the default one, we needed to track the per field statistics because we're handing stuff to the default postings format, which doesn't know about the tricks we're doing above it. It thinks it's getting one field with all these terms with these weird bytes at the end that it doesn't really care about. So we're playing tricks above it, and we need to do some bookkeeping as we pass it on through. And one of the things we definitely needed to do for performance was the postings format gives you an opportunity to the option of overriding the merge method, which occurs when segments merge. And because the default algorithm will be very slow based on what we're doing, but because we know internally how the data is actually put into the underlying wrapped postings format, we overrode merge so that we can have an optimized version of it that was much faster. So we basically did our own merge instead of using Lucene's default merge of the postings format. Next.
So just a summary of the wins of this approach. So now we reach almost all the objectives we had. We are closer to the performance of a single field. We reduce the number of segments and divide them by 2. And the memory is really decent, and we don't see any increase comparing to the previous situation. And for the second phase of merging and computing scores, we also benefit from the reducing of the number of segments. And as David just detailed, the slope is slower with the number of fields for scoring.
I'll super briefly review some modifications. We made plugins to Lucene's API that fit nicely. We also have a fork of Lucene internally where we've made some changes. I think this is one of the biggest downsides to the overall approach we made. And some aspects of the fork are there because of some of those caches that Yannis mentioned about the knowing which fields the postings format needs to know in advance which fields it's going to see. So we did some tricks to make that happen. And we made some modifications to Lucene. Over time, we may do some other changes to potentially reduce how much we need to fork Lucene. That's the kind of the undesirable aspect. Next.
So let's conclude with a few performance charts. So we used, in Salesforce, we have some dark clusters to do some dark experiments and compare brand new code in production. So this chart shows the query latency observed in production. And we see the yellow curve was the catch-all field strategy. Usually our queries in production are really fast. You can see it's under 5 milliseconds in mean. And with our new strategy, we see that the average is not degraded that much. We can see from time to time a 2-time factor, but we are pretty close to our goal. And the second chart shows the average query latency depending on the number of fields in the query. And we see that the slope is really smaller than before. So the x-axis shows the number of fields. So in the middle of the x-axis, you have the 150 points. And we can see that before we were around x20 factor, and now it's simply a x2 factor. Of course, we have some trade-off to consider, and the CPU usage is more than before, but it's an acceptable factor for us. We also monitor the GC usage. So it's pretty low today. We have few garbage collection pauses, and we keep the same shape than before. So it's a great milestone. Today, we are currently deploying it in production, and for sure, it empowers the Salesforce platform. But it's just the beginning of this story, because we will now be able to deliver all this information for real events and build per customer model, relevancy model, and to be even more accurate and know what our user really want to search. Thanks a lot for your attention.